Wormholes often feature prominently in science fiction, allowing for interstellar travel on human timescales. In reality, however, using wormholes as a means of traversing space, or time, faces a critical obstacle. They are inherently unstable. To stabilize a wormhole, one would need materials with negative energy density, at least in some reference frame. No known form of classical matter can achieve this, although it is conceivable that quantum fluctuations might provide the necessary exotic conditions. In the film Stargate and its related television series, ring-shaped devices, stargates, can maintain an artificial wormhole for only about 38 minutes. Extending this duration would require immense amounts of energy. In actuality, when a particle enters a wormhole, its presence is theorized to trigger fluctuations that could cause the structure to collapse. A wormhole can be thought of as a tunnel through the fabric of space itself. Much as one might choose to tunnel through a mountain rather than climb over it, a wormhole could provide a shortcut from one location in space to another. Remarkably, if such a wormhole could be formed and manipulated, say by placing one of its openings near a black hole, where time runs more slowly, it might not only connect different points in space but also different points in time, effectively acting as a time machine. Of course, this remains purely hypothetical. We have never observed a wormhole, and even if one existed, we do not know whether it could be traversed safely. Theoretically, black holes might serve as portals that generate wormholes across the universe. Current thinking, however, suggests that any resulting wormhole would be prone to rapid collapse. Consider two black holes. Each can be described by a quantum mechanical theory on a boundary. If these two theories are entangled, they become connected by lines of quantum entanglement. Mathematically, this entanglement corresponds to a wormhole, an Einstein-Rosen bridge, connecting the two black holes. In this way, quantum entanglement might correspond to the formation of wormholes. This concept, known for decades, arises naturally from Einstein's theory of general relativity. Wormholes, or Einstein-Rosen bridges, are hypothetical shortcuts through spacetime connecting distant regions, and potentially even different epochs in time. Although general relativity allows for their existence, the consensus holds that they would be highly unstable because they are, in essence, two black holes in direct contact. For an object falling into a black hole, classical reasoning suggests a grim fate. As it approaches the event horizon and moves inward, gravitational forces intensify, stretching and ultimately destroying it. Observers at a safe distance, however, would perceive the infalling object's time slowing down as it nears the black hole's edge, a direct consequence of general relativity's prediction that gravity warps both space and time. Gravity, in essence, is the curvature of spacetime, affecting how clocks tick and how objects move. If wormholes exist, they might allow for faster-than-light travel in an indirect way. Locally, no object exceeds the speed of light. But if a wormhole provides a shortcut, effectively reducing the distance between 2 points, travelers might cross vast distances faster than a light beam traveling outside the wormhole. This does not violate relativity since, at each point along the journey, the traveler never surpasses light speed. The wormhole geometry simply changes the rules of the game. Despite decades of research, the main challenge remains. Wormholes are believed to be violently unstable. Before recent theoretical work, scientists assumed that maintaining an open wormhole would require hypothetical forms of exotic matter with negative energy density, something no known physical process can produce in large amounts. Without such exotic matter, a wormhole would pinch off nearly as soon as it formed. However, new theoretical approaches may offer a glimmer of hope. Physicist Pascal Koirin, for instance, explored wormhole stability using the Eddington-Finkelstein metric rather than the traditional Schwarzschild solution. His results suggest that a particle might cross from one side of a wormhole to the other without encountering any mathematical inconsistencies, implying these tunnels could be more stable than previously thought. This is intriguing because general relativity primarily describes gravity and not other fundamental forces or quantum effects. According to astrophysicist Paul Sutter, Koirin's work doesn't guarantee traversable wormholes, but it does show they may not be as catastrophic as initially feared. If future research and theoretical developments confirm the possibility of stable wormholes, they could serve as cosmic bridges, enabling travel over immense distances, and potentially even through time, without the need for faster-than-light speeds. Still, It's important to stress that no wormhole has ever been observed, and the stability and traversability issues are far from resolved. The connection between wormholes and quantum entanglement, as well as the interplay between gravity and quantum mechanics, remains an active field of research. Scientists are working hard to understand these exotic structures, if they exist at all, and to determine whether they can ever be used by hypothetical advanced civilizations for travel or communication. For now, wormholes remain a tantalizing possibility confined to equations and speculation. They capture our imagination and appear frequently in science fiction, inspiring movies like Stargate. Perhaps someday we may discover that wormholes are real and can be stabilized, opening the doorway to distant galaxies. Until then, we continue to rely on theoretical work, simulations, and observations of the cosmos to guide us forward. Thank you for watching. If you enjoyed this deep dive into the physics and speculation surrounding wormholes, please consider subscribing and enabling notifications so you never miss future discussions about the mysteries of the universe.